Section 21.3, the motion of a charged particle in a magnetic field. First, let's recall what we saw for a charged particle in an electric field. If we had two plates with opposite charges, one positive, one negative, that sets up an electric field that points from the positive toward the negative. If then a positive charge comes in with some velocity that's initially perpendicular to that field, the velocity will eventually be redirected by this electric field until it's moving in the same direction as the electric field, because the force of the electric field is always lined up with the electric field. Positive charge, it's in the exact same direction. If it was a negative charge, it would also bend around, just come around to the positive plate instead. The magnetic field, it turns out, looks a little different in how it comes out. We have a similar setup with a north pole and a south pole, just like our positive and negative plates. That would create a magnetic field that points from the north to the south pole. We can then bring in that same positive charge with a velocity coming perpendicular to the magnetic field. But now, instead of the force being in the same direction as the magnetic field, the force is perpendicular to both the velocity and the magnetic field. The force is going up. So the charged particle will actually start to bend its path and travel more and more upward. But even when it's traveling upward, that still won't be in the same direction as the force due to the magnetic field. The force due to the magnetic field is still perpendicular to the velocity. It's now pointing to the left. Notice that the force created by the magnetic field is always going to be perpendicular to the velocity. This tells us something about the work. The magnetic force, it turns out, cannot do work on a charged particle. The electrical force that we've seen before can do work on a charged particle. It's able to exert a force that's in the same direction as motion of the charged particle. But the magnetic force is only going to exist perpendicular to the charge. So it's not changing the velocity of the charge. It's not doing any work on it. It's just changing the direction of it. Now that we know a little bit about how the magnetic force and the electric force can both change the particle's path, let's take a look at a conceptual example. Conceptual example 2, a velocity selector. Velocity selector is a device for measuring the velocity of a charged particle. The device operates by applying electric and magnetic forces to the particle in such a way that these forces balance. How should an electric field be applied so that the force it applies to the particle can balance the magnetic force? And that's given, shown as a setup over here, where we have a charged particle entering between two plates of a capacitor, as well as entering a magnetic field that is into the paper. Note that the direction into the paper is shown with X's. The other direction that you'll often see is out of the page or out of the screen, and that's shown with a row of dots. So these represent a three-dimensional view, and the way that you can think about this is with an arrow, right? If you shoot an arrow, then if you see it coming at you, all that you see is a dot coming at you. But if you look at it going away from you into the page, then that's where you can see the fletchings on the arrow, and those will make a little X as it flies away from you into the page. Now that we have that set up, I'd like you to take a look at this problem and come up with an answer between A, B, C, and D before you move on. So go ahead and pause the video now. Right, trusting you did that. If we want to figure out the direction of the electric field, we need to first figure out the direction of the magnetic force. So if the charged particle is just entering a magnetic field, if we forget the electric field for a moment, where it's going into the page, how can we figure out the direction of the magnetic force? That's where we have our right-hand rule. And if you're anything like me, it's easy to get all the letters confused. So I made handy little labels. You can do this for yourself, or you can make a picture that shows all the different fingers that you can remember. Because I'll tell you, if you have them labeled, these become way easier. Let's try it out. All right, so I want to line up my thumb with the velocity, and then I need to get the magnetic field going into the page or into the screen from my view. So the only way that I can keep my thumb pointing to the right and my finger going into the page is if I rotate around, so my thumb is going to the right, magnetic field going into the page, and that tells me that the force is going to be up, right? That's coming out of the palm, if you prefer the palm view, that we then have that magnetic force is going up on this charged particle. And we can show that. Right, so if we want the forces to balance, it's going to be the direction of the electric force. The only way these can balance is if the electric force is going down. Great. Now, if the electric force, for that to go down, what's the direction of the electric field needed? To figure that out, we need to take a look at this charge. So because this charge is positive, that tells us that we want an electric field that is going in the same direction as the electric force. If this was a negative charge, then to get a downward electric force, we'd have to set up an upward electric field. That feels a little backward. That's an important thing to understand and wrestle with. So that means we need an electric field going from the upper plate down to the lower plate. That's described here in C. We could even think about how we'd want to charge these. Which of these plates would be positive, which would be negative? Well, remember the electric field lines flow out of the positive and point into the negative. So that even tells you about the relative charges there. And we see that the answer is indeed C. We want to keep looking at this idea of how magnetic force can act on a charged particle and what it means for its motion. So because the magnetic force is always perpendicular to the velocity, if a charged particle remains in a uniform magnetic field, then the charged particle is actually going to start traveling in a circle. We can show this at any of these points. If you start at point 1 and we have the magnetic field is going into the paper, the velocity is to the right, so the force is up. This is like the last one we just saw. But if the force is up, that particle is not going to keep going to the right. It's going to get pulled upward until it starts moving up. This is where it is in part 2. Now that the velocity is up, the magnetic field is still into the page, which means the force is now to the left. That means the velocity is not going to keep going up. It's going to whoop by the top of the circle, right? The velocity is now going to the left. Magnetic field still going into the page, and the force is down. And you can do this tracing out the entire circle, depending on your flexibility, right? At some point you have to reset. But the force is always inward, and it creates this circular path. Now, circular paths we've studied a bit before. If there's a circular path with a set speed, the speed is unchanging, we know the acceleration. Remember the acceleration of a circular path? That's our centripetal acceleration, v squared over r. And we can bring this back to Newton's second law once again. So Newton's second law, F equals ma. The force here is just the net force, which is an inward centripetal force. It's equal to the mass times the centripetal acceleration, v squared over r. Now if we plug in our magnetic force with an angle of 90 degrees, because they are perpendicular in this case, we get that that magnetic force is Q times V times B, and that's equal to m v squared over r. This allows us to then solve for the radius. We can notice that the radius of the circle, how big the circle is set by the mass of the particle, how fast the particle is moving, divided by the charge, and divided by the magnetic field. So if you have a more massive particle, it's going to be a larger circle. If you have a smaller charge, that will also create a larger circle because there's less inward force pulling it in. Let's see how this plays out in a conceptual example. Particle tracks in a bubble chamber. The figure shows the bubble chamber tracks from an event that begins at point A. At this point, a gamma ray travels from the left, spontaneously transforms into two charged particles. Particles move away from point A, producing two spiral tracks. A third charged particle is knocked out of a hydrogen atom and moves forward, producing the long track. This is an example of evidence that particle physicists would look at in a particle accelerator. So, for instance, the Large Hadron Collider, LHC, or other experiments where they are looking at particles and how particles can transform into other charged particles. And we want to know what they transform into. And based on what they transform into, that can tell us about the original particle. So for this picture, the magnetic field is directed out of the page. We want to determine for all three particles the sign of each particle and which one. So I want you to think this through, come up with an answer before you move on. Go ahead and pause your video now. All right, did you pause it? I'm hoping so. Well, let's figure out we know that the charge is coming in from the left. That tells us it's moving to the right, as shown here. And the magnetic field, it says, is out of the page. And that's what's shown with the dots, as before, so we can figure out the direction of the force. So if our V is moving to the right, magnetic field's coming out of the page this time, then now our force is coming down. And that's what's shown here. The force is down. Now, one of these does have a force going down. That's particle 2. The others, the force is going in the opposite direction. How could the force be going in the opposite direction? Maybe if they are negatively charged, right? We could double check this with our left-hand rule. We have the velocity, magnetic field coming out of the paper, then the force is up. It's in the opposite direction as what we have when we use the right-hand rule. So that tells me particles 1 and 3 are negatively charged, while particle 2 is doing what we'd expect for a positive charge. It has the force going down. Now, how do we figure out which one's moving the most rapidly? Well, that's where we can think about that equation we just got. R is equal to mass times velocity all over Q and B. All of these have the same magnetic field on them. And we don't know anything about the mass of the charge. But what we do know is that the radius is different for several of them. And that's enough to tell us that the velocity is also different. So if we want a large radius, then we also want a large radius. Right, for most rapidly, it's going to be a large velocity. So a large radius would correspond to that. Which of these has the largest radius? Well, 2 looks slightly bigger than 1, but notice 3 is the biggest radius of all by far, right? This is a huge circle that can't even begin to fit on this page. And so this radius is way, way bigger. So particle 3 is moving the most rapidly. This is one example of how these ideas apply to particle physics, but there's a more biology, chemistry example in application of these ideas. So you'll want to check it out.